In this video, I would like to talk about transforming normals. This is not a general topic, but if you have written a 3D program, you are probably my audience. Let's say that you are me and you are working at a hardware company. You are developing large-scale data visualization software. Your goal is to show terabytes of data. It's not an easy task. But anyway, your software started by showing a single triangle. While you were operating on a triangle with a model matrix, you found something weird. By the way, a model matrix is a matrix applied to a graphic primitive. For example, it scales, rotates, and shears your primitive, which in your case is a triangle. When you were in the university, the internet was still young. You wrote a program to play a game. Rotating a polygon is linear algebra. You learned about the 4x4 matrix. To shade a triangle, you need a normal vector. A normal vector indicates the direction of the triangle face. A normal vector is perpendicular to the triangle face, like this red arrow. You put the x-axis and y-axis on the triangle face. You see your right hand. If your thumb points to the positive x-axis and your index finger points to the positive y-axis, then the positive z-axis is designated by the middle finger. This is the famous right-hand rule. The normal looks like this in 2D. You assume you can use the model matrix to transform everything, including normals. When you uniformly scale a line, you don't have a problem. The rotation is also fine, but you found that shearing has a problem. When you scale the x direction, this assumption is also broken. You asked your colleagues, how can we transform normals? They answered that you need to use the transpose of the inverse of your model matrix. When you tried it, it worked. But why? A question. Why is transforming a normal the transpose of the inverse of the model matrix? Or why is the intuitive transformation wrong? You asked your colleagues, why? The answer is, I don't know, but if you know, let me know, please. Wikipedia has a section about transforming normals. You look at the equation. Yes, the equation seems right. But are there any more intuitive explanations? So you start exploring. It is always good to go back to the basics. What is a normal vector? Wait, you can even rethink the idea of a vector. What is it? At least it is called a normal vector, but it doesn't follow the behavior of the model matrix. Can you recall that how you compute the normal vector? A cross product? Yes, but the cross product is one of the type of vector products which depends on 3D. You, which is me, try to stick to the 2D model as long as it works. When you draw some normals, you realize something. The normal doesn't exist by itself. You always need to draw a surface when you draw normals. A normal vector depends on the surface. Your first clue is that a normal vector is attached to a surface. At some point in the triangle, you can imagine a small patch of the triangle. Then the normal is calculated based on that patch. This patch seems redundant, but you can think about normals on a surface that isn't flat too. You also notice that the normal is not a single arrow. There are many. It's a vector field. A normal needs a surface. In fact, a normal depends on a surface. You realize you know such a mathematical object. It's a function. A function gets inputs and produces something, its output. There is a function that gets a surface and a position as inputs, and then output normals. In this case, the function describes the normal, so you write the function as m instead of f. The function is the plane equation. It gets a vector and output a scalar value. Let's visualize the normal as a function. One problem is how to show the plane constant. Let's start with t is equal to 0. Here's a triangle, a patch and normal, a patch and normal, and a patch and normal, and more. But this is too busy, it's not helping, and this is only the functions d is equal to 0 case. One thing you feel weird about is drawing a function as an arrow. Maybe you can omit the arrows. Let's try again. It's a plane, no surprise, since we used the plane equation, and you can visualize other d's. This is d is equal to 1. Now d is equal to 2, minus 1, and minus 2. This is the plane equation. You put arrows oriented to d is increasing direction. Now you have doubts whether a normal vector is a vector. Let's back to 2D. The plane equation in 2D is this. You can write this as a dot product. Here is a matrix form and its components. You wonder, what is the difference between the dot product and the matrix form? The component form looks the easiest. And a small discovery. The normal in the matrix form is a row vector. If a normal is a column vector, like a usual vector, this is a transposed form. A transformed normal has a transpose. It might be related or it might not be. Here is the plane equation. Again, visualizing the plane constant d is a problem. But we can use the same method as in 3D. Let's start with d is equal to 0. You need a concrete example normal n. You choose 2, 1, because your troublesome triangle was inclined. Let's plug the components into the equation. You could continue with v1 and v2, but this is on an xy plane. You are more familiar with x and y, so this became 2x plus y is equal to 0. Solve for y is equal to minus 2x. Indeed, this line is perpendicular to the normal. When d is equal to 1, the procedure is the same. But this d changes the location of the plane. Plug the components into the equation. You got a line equation. This line is also perpendicular to the normal. It is the same story for other d's. In 2D case, d is related with the y-intercept of the lines. That's how the plane location changes. You see, they are a stack of lines. You put small arrows to indicate the d's increasing direction. It's like the line that describes the height of a mountain. I finally feel something about this function. A discovery. A normal function is a stack of lines in 2D, and a stack of planes in 3D. The density of the stacking lines is related to the normal components. When we solve the plane equation for x, the coefficient of d is 1 over 2. Put a basis vector e1 for the x direction. You see this vector pass through two stacks. It's reciprocal of the coefficient. When we solve this for y, the coefficient of d is 1 over 1, which is 1. Put a basis vector e2 for the y direction. You see this vector pass through one stack. This is also reciprocal of the coefficient. You recall something similar to the normal function. It's counter lines. A map has lines connected to the same heights. A normal is a function that gets a vector, and counter lines are a function that gets a position vector. A normal outputs a scalar, counter lines output a scalar value, height. A normal indicates the direction of the face. Counter lines indicate the heights and slopes, like this figure, where the dense lines show a steep slope. Now you compare between vector and normal. Normal and vector are very similar. That's the reason you thought they are the same kind. A vector is probably an object. You still don't know what exactly the vector is. A normal is a function. You know that. A vector is not a function. That means, say, they live in different places, but they have a relationship like this. You think they are similar, but not the same. The clue is a relationship. You hope this clue gives you something. How can you find the transformation from this clue? you try to write all the detail. Here's your plan. 1. Write a vector as a linear combination of the basis. 2. Write a normal as a linear combination of the function. 3. Find the relationship between a vector and a function. 4. Maybe this gives you that transformation. And 2 and 4 could be tricky. Let's see how we can write the vector by a linear combination of bases. We have a basis e1 and e2 and the vector v. The components of v are -1 and 2. We can decompose them for each basis direction like this. Then we can factor out the components. You see 1, 0 and 0, 1 are our bases e1 and e2. So we can write this as -1 times e1 plus 2 times e2. This is a linear combination of e1 and e2, which means we have a form of multiplies of e1 plus multiplies of e2. Let's see the components on the coordinate plane. V's x components are here, which is -1 and -1 times e1. V's y components are here, which is 2 times e1. You know this well. This is easy. You can decompose a vector to basis components. You are familiar with this. This was a linear combination representation of a vector, but can we do the same to the normal function? Now let's try this on the normal function. This is your normal function. When d equals 0, the normal vector is like this, but you don't use that representation. As a matrix form, the normal function is a row vector. You can decompose it pretending there is a basis x component only and y component only. Then we can factor out the coefficient. You call the basis 1, 0, epsilon 1 and 0, 1, epsilon 2. The coefficient for epsilon 1 is 2 since the e1 goes to the line stack twice. The coefficient for epsilon 2 is 1 since the e1 goes to the line stack once. Now you can write the normal function as a linear combination of the bases. Here is a normal function and its visualization. If you can decompose it to x and y direction, this is x component 2 times epsilon 1. This is y component 1 times epsilon 2. This is the linear combination representation of the normal function. In this video, we saw what is a normal. I hope you saw the normal is not a usual vector, it's a function. Then we saw a linear combination representation of normal function. At this point, you still don't know how to transform the normal function. However, now you know a bit more about the normal, and you can represent the normal function as a linear combination of bases. Your plan is to find the transformation of the basis, since the basis is simpler than the general form. You will continue to explore this. See you next video and thanks for watching.